got a sum over a sum.
Oh, right.
So that's good. This is like, oh, you said this is like J, and this is like J.
Yeah, I need to catch up with this. I did one.
I'm going to start writing units.
I didn't write the notes.
Finally, that's the I'm just trying to write down.
I was doing the exercises yesterday. Just
It would take me like 2 pages of work.
The things are the exercises, they're already past the questions.
In what?
I think it kind of hints into what the
Oh, you mean like use?
Still
trying to get to the finite.
Yeah, no, I've been trying to use what it does.
Don't come across as too enthusiastic. Otherwise,
Yeah.
you're in a challenge when we don't.
Let's start. Today, before we begin with the lecture, I'm going to show you the solution to the exercise about Hausdorff measures, because this is the only exercise about Hausdorff measures that you had, and I just want to practice it again with you. So this is about the Hausdorff measure and the Hausdorff dimension. Here I've written down the definitions once again for you. And the first exercise was to show that if for some d0, h d0 of A is finite, then hd of A is 0 for every larger d. Okay, so intuitively, if the d0 dimensional volume of a set is finite, then the d dimensional volume of the set is 0 as soon as d is larger than d0. And the solution to this is just write down the definition of the Hausdorff measure and use that explicitly. So okay, so assume that hd0 of A is finite. Then by definition, if you look at the definition over there, this means that there exists constant such that h d0 delta of A is less than this constant for every delta positive, right? Just because HD is the soup of all the HD delta. Okay, now we've gone from HD to HD delta, and now we have to use the definition of HD delta. So we have to use these coverings of A. And in fact, okay, what do we know? We know that h d0 of delta of A is bounded by this constant. So because h d0 was defined to be an infimum over these coverings, this boundedness implies that there exists a family of sets. So there exists a covering of A by some sets AI with diameter AI less than delta, and sum I equals 1 to infinity diameter of AI to the power d0 is less than, let's say, c plus 1. Right, this thing is bounded by c, but this hd delta is defined to be an infimum over these sums. So if we increase the upper bound by a little bit, say by 1, then we can always find AI such that this sum is less than constant plus 1. Okay, but now we can do the following. So up to now, we've only taken D0, 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 because that's something we know something about. Now let's take HD delta of A, and we want to show that this is 0, if we let delta go to 0. So HD delta of A is less than or equal to sum I equals 1 to infinity diameter of AI to the power D, right? Because the AI form a covering, and by definition HD delta is just the infimum over these sums, so it's less than this sum, where we use the power D now. And now just use the fact that D is larger than D0. So this we can write as sum I equals 1 to infinity diameter of AI to the power D0 times diameter of AI to the power D minus D0. And now by assumption we know that this exponent D minus D0 is positive. So what we can do now is we can estimate this by just, okay, first we can just replace this diameter of AI by delta if we want, because the diameter of the AI is less than delta. And this diameter to the power D0, we just leave it there. So we get diameter AI to the power D0 times delta to the power D minus D0. And now we can use this inequality, right? The sum of the diameter of the AI to the power D0 is bounded by C plus 1. Here we precisely have this sum with power D0, so this is less than delta to the power D minus D0 times C plus 1. Okay, but this is nice. Now we know that HD delta of A is bounded by a constant times delta to some positive power. So now if we let delta go to 0, this will go to 0. So this implies that limit delta going to 0, HD delta of A is less than limit delta to 0, delta to the power D minus D naught, C plus 1, which is 0. But now, by definition, this left-hand side is just equal to HD of A. So we've shown that HD of A is 0. So this is part A. Are there any questions about part A? Okay. Okay, so let's do part B now. Part B was probably the most difficult of these four. It's to show that the Hausdorff dimension of any set in Rn is always less than n. And one possible solution is this. So, by definition of the Hausdorff dimension, it's enough to show that HD of A is 0 for every D larger than n. Right? Because then this infimum of D where this is 0 has to be n or less than n. Okay, so we want to show this. HD of A is 0 for every D larger than n. And you can do this the following way. So start with a number that m be a natural number. And consider the cube Qm, which has edge length m and is centered at 0. Okay, so this, not surprisingly, looks like this. So this is Qm. And the size of this cube is determined by m. Now, next, choose another number k, and choose a covering. Of this cube Qm by smaller cubes. So by cubes of edge length 1 over k. So what we do is this: we have this large cube Qm, and we just decompose it into many small cubes. Of edge length 1 over k. Okay? And these are the AI. So each of these small cubes is one of the AI. And now I want to use this in the definition of the Hausdorff measure. And this number 1 over k will play the role of this parameter delta in HD delta. So that's the idea. Okay, so far we've only looked at this cube. We haven't even talked about this set A that's given in the exercise. But now, because these small cubes cover the large cube, we know that these AI also cover Qm intersected with A, right? Certainly. And now we want to look at these kind of sums with these AI.
Should A be a subset of Qm?
No. A is, I'll deal with that later. You spotted something that's quite right. So A is an arbitrary Borel set. And first what I want to do is deal with the intersection of Qm and A. and later I want to expand Qm to conclude something about A. So A does not have to be a subset of the cube. Okay, so now we have this. We know that this is a cover for Qm, the intersection of Qm and A. Then this HD delta for delta equal to square root of n divided by k of A is can be estimated by the sum of the diameters of these AI to the power d. Right, because this is the infimum and so on, and the diameter of these AI is less than square root of n divided by k. Just because the diameter of these AI is just the diagonal of these little cubes, but the diagonal of a cube is always square root n times the edge length of the cube. So the diameter of these AI is less than this, so I can choose this as my delta. And now how many of these cubes do we have? We have m times k to the power n. Right, because the edge length of the small cubes is 1 over k. So in an interval of length 1, I can fit k of these little cubes. So in an interval of length m, I can fit k times m of these little cubes. And then to fill the entire cube, I have to take this to the power n. So this is how many small cubes we have. So we have this estimate for the Hausdorff measure, and that's something we can work with. Because now, this is just the same as I equals 1 to m k to the power n. Okay, so the diameter of these things, I already said it. We have an explicit formula for that. It's just diameter to the power d is n to the power d over 2 times k to the power minus d, right? Just square root n divided by k to the power d. But now, this is always the same number. Nothing here depends on I. So this sum is just this number times mk to the power n. So this is just n d over 2 k to the minus d times m to the power n times k to the power n. And now this is n d over 2 m dn. This is just some constant times k to the power n minus d. And now remember what we wanted to show was that hd of a is 0 for every d larger than n. So if d is larger than n, then this exponent of k is negative. So if we send k to infinity, this goes to 0. And here, sending k to infinity is the same as sending this parameter delta to 0. So we get an estimate for this Hausdorff measure from this inequality. So from this, it follows taking k to infinity. Oh, this is not a, by the way. This is a cap qn. Sorry. So now taking k to infinity, this implies that h d of a cap q m is 0. because this upper bound here goes to 0 as k goes to infinity. Okay, so now we know that if we fix a cube, then the intersection of that cube with A has Hausdorff measure 0 if D is larger than N. And now we can do the following. If we look at HD of A, the entire set A, then this is the same as HD of the union M equals 1 to infinity Q M cap A, right? Because these cubes just become larger and larger and exhaust the whole space. But now, hey, this is a countable union of measurable sets, so we can use subadditivity of the Hausdorff measure. So this is less than or equal to H, the sum M equals 1 to infinity H D of QM cap A, but all of these are 0 because that's what we shown. So this is 0. And that's the proof of part B. Yes?
You said earlier that so at the bottom it says AI is a cover of QM intersection
Yes.
A, and you said we weren't allowed to necessarily assume that A was a subset of QM.
Yes.
How come we can take a cover of it if it's not a subset? Do the AIs make up A?
No, the AIs make up QM.
Oh, okay. Right.
So, so at this stage, we're not even intending to cover all of A. We just want to cover this intersection.
Okay.
Because we just want to conclude something about this intersection.
All right. Okay.
And only in the last step, we conclude something about A by taking the union of all these cubes.
I was thinking they were related because one's AI and one's A, but no, it's fine. Thank you for explaining.
Any other questions? Okay, so this was part B. In part C, the task was to show that if A has non-empty interior, then the Hausdorff dimension is N. So the same dimension as the entire space. This was rather simple if one uses a proposition from the lecture. So again, if you look at the definition of the Hausdorff dimension, to prove C, it's sufficient to show that Hn of A is non-zero. All right, because then this infimum, where it is 0, has to be larger or equal. But in B, we've already seen that it has to be less than or equal to n. So then it has to be equal to n. So it's sufficient to show that the n-dimensional Hausdorff measure of A is non-zero. But now, the n-dimensional Hausdorff measure by a proposition from the lecture is just proportional to the Lebesgue measure of A by proposition 3.28. But now the Lebesgue measure. Okay, so now we have to use the assumption, right? A has non-interior. And we know that the Lebesgue measure of such an A must be non-zero, because if A has non-empty interior, it means that it contains some cube of edge length epsilon for some epsilon. So, and we know what the Lebesgue measure of such a cube is, right? It's just edge times edge times edge. So it's definitely non-zero. So because the Lebesgue measure of such a set has to be non-zero, the Hausdorff measure has to be non-zero. So Lebesgue measure of A is non-zero since A contains a cube of size epsilon for some epsilon positive. So part C more or less follows immediately from this proposition that says the n-dimensional Hausdorff measure is equal to the Lebesgue measure. And part D, if A is countable, then the Hausdorff dimension must be 0. This is very similar to things we've seen in the lecture. This is very similar to showing that the Lebesgue measure of a point is 0, for example. So, proof of D. One can start by showing that HD of a single point is 0. Does anyone know how we can do this? Using the definition.
Just cover it by a cube, small side length, and the length of 0.
Right. So, yeah, that's exactly right. So this is 0 because this point x, for example, this is a subset of the cube x minus delta, comma x plus delta, and then to the power n. And now the diameter of this is again square root of n times the edge length, which is 2 delta. So if we use this in the definition of the Hausdorff measure, then we get that HD delta of this point x can be estimated by where this sum now just has one term, which is the diameter of this cube to the power d. So square root n times 2 delta to the power d. And I mean, square root n is just some number, 2 is just some number. So if we send delta to 0, this will go to 0. So sending delta to 0, we conclude immediately that this HD of a single point x must be 0. Okay, now how do we go from a single point to a countable set?
Dick union. Dick union.
Right. Yeah, every countable set can be written as a countable union of single points, and then use additivity, for example. Okay, so this holds for every positive d. And therefore, I need more space. Okay, so now if we have some countable set, then HD of this countable set is the same as HD of union n equals 1 to infinity of these single points as n, xn. And now you can use additivity or even sub-additivity if you want. And then this is sum n equals 1 to infinity HD of just xn. And each of these is 0. So you get 0. So this shows that for every positive d, HD of a countable set is 0. So if you take the infimum of all these d's must be 0. So the Hausdorff dimension is 0. Any questions about this last exercise? Okay, so this was just to repeat Hausdorff measures again. And now let's continue with the lecture. Last time we started defining integrals. And we started by looking at these so-called simple functions, which by definition were just functions which are constant on a measurable set, and then sums of such functions. And then we studied the simple functions for a little bit, and then we defined the integral for such a simple function. And the very last thing we did last time was to define the integral of a non-negative measurable function. So very briefly, definition 4.14 was the definition of the integral for simple functions, which was just integral x phi d mu is sum I equals 1 to k c I mu of ai, where these coefficients ci and these sets ai came from the definition of simple functions phi. I'm not going to write all of this again. And then the next definition was for measurable functions. So this definition was integral x f d mu equals sup integral phi d mu such that phi is simple and phi is less than f. And this definition was for f from x to 0 infinity measurable. And the important thing here is, don't forget, if in this definition f has to be non-negative. So far we only know how to integrate non-negative functions. We'll extend the definition later, but up to now integrals are only defined for non-negative functions. One thing, okay, and then now we continue. So one remark that we have to make immediately is that, well, here there are two different definitions of an integral, right? The second definition holds for every measurable function. The first definition holds for simple functions. But what if in the second definition f is a simple function, right? Simple functions are measurable. So for simple functions, we can use either this definition or that definition. And then it would be weird if we got different results. So the first remark is that if f is a simple function, then these two definitions are the same. They give you the same result. So everything here is consistent. And if you want to see a proof of this, I think it's done in the lecture notes. Okay, so everything's well defined. Everything's fine. So, okay, and now we're just going to study this integral and derive some properties. So the next lemma establishes monotonicity of these integrals. So first, if phi psi are simple functions, and phi is less than psi, then integral phi is less than integral psi. And the second is the same for measurable functions. So if f, g are non-negative measurable functions, and f is less than g, then integral f is less than integral g. and the proof makes use of these definitions. So point 1, monotonicity for simple functions of the integral. Basically it follows directly from this formula. Last time we had a remark. That said, if you have two simple functions, then these sets AI, where these functions are constant, you can choose the same AI for both functions. And we're going to use that now. So we choose common sets. AN such that phi has the representation sum I equals 1 to k Cn characteristic function of An, and psi has a similar representation I equals 1 to k Dn chi An. Right, and the important thing is that this An is the same as this An. So we chose a common set for both functions. Then because these An are the same and phi is less than psi, we can conclude that Cn is less than Dn for every n. And now we just use the formula for the integral. This is easy. So because Cn is less than Dn, we can conclude immediately that the sum Cn mu of An is less than sum Dn mu of An. And of course this is the same as integral phi is less than integral psi. So this is point 1. For the second claim, so the same thing for measurable functions. Well, we have to use this definition. So we have to approximate f from below by simple functions. Okay, so in the second claim, we have two measurable functions, f and g, and f is less than g. And now what we do is we choose a simple function with phi less than f. Then phi is also less than g, right? Because f is less than g. And let's call this star. So this definition of the integral, that's star. So by the definition of this integral, it follows that integral phi d mu is less than integral g d mu. Right? Because phi is less than g, we can use it in this definition, and because the integral of g is the supremum, it has to be larger than the integral of phi. So we get this, but we can do this for every simple function which is less than f, right? We always get the same inequality. So we can just take the supremum over all phi, which are less than f, and then the left-hand side becomes the integral of f. And this proves the second claim. Okay. Are there any questions about this lemma? Okay. Okay, so the next theorem, I've actually advertised this a couple of times. This is one of the most important theorems of the lecture. This theorem tells us something about limits of sequences of functions and how the integral behaves under that. So, start with the measure space. And then assume we are given an increasing function sequence of measurable functions. And of course non-negative, because that's the only thing we can deal with up to now. Measurable and finally assume that Fn converges from below to a function f. Then integral f d mu is the same as limit n going to infinity integral Fn d mu. So in other words, if we have a sequence of functions and we know that it's increasing and we know that it's non-negative, then we can compute the integral of the limit by first computing the integral of the Fn and then taking n to infinity. And this is so important because it just applies to many situations. Maybe you remember in the very first lecture, I tried to motivate why we're doing measure theory.
Yeah, because I heard like all sorts of like, I don't know, horror stories about.
That's the thing. In my life, I want to get paid, get laid, Gatorade.
Supervisor. And he's kind of like, you know, not hitting guy. Sounds like
That
we really
would
don't
get
like him.
Gatorade, that's really what I'm about.
Yeah, he's quite eccentric.
Okay,
Yeah.
let's continue. So, before we start the proof, we have one short remark, and I just wanted to tell you this theorem is also called the monotone convergence theorem. That's what people usually call it. So if in any book you see monotone convergence theorem, they mean this theorem. Some people call it Bepo-Levy's theorem, but it's more common to call it monotone convergence theorem. Okay, the first remark is this assumption that the sequence is increasing, that's essential. Without this assumption, the theorem would be false. And on the new problem sheet, one exercise will be to construct counterexamples that show this. The second remark is for later reference. So this increasing assumption is essential. The assumptions that the functions be non-negative can be replaced by a different assumption, but only that applies only later when we've defined the integral for all possible functions, not just positive ones. So the assumption f and non-negative can be replaced by the following assumption: supremum and integral fn d mu is finite. Okay, so if you assume this, then this theorem still holds even if the functions are allowed to be negative. Yeah. And if you assume non-negative, then you don't need this. So the this limit could be infinite if you want. Then the integral of f is infinite. Okay, so this is just for you. If you see someone else apply this theorem to negative functions, then you know that they probably use this assumption, and then everything's fine. Okay, the proof. Goes as follows. So to show that these two sides are equal, we'll show both inequalities. So this is less than this, and this is larger than this, or equal. And then they must be equal. And as always, one inequality is easy to prove, and the other one is difficult to prove. So, by f, we denote the pointwise limit of these fn. Could be infinite, certainly is non-negative. Then we know that f is measurable. By lemma 4.10, which we proved last time. Remember, lemma 4.10 said something like limits of measurable functions are measurable. So this applies in this case. Now, the monotonicity of the integrals that we just proved implies that integral fn d mu is less than or equal to integral f d mu and also integral fn d mu is less than or equal to integral fn plus 1 d mu. Right, that just follows from the monotonicity of the integral, because f is an upper bound for all the Fn. So we have the first inequality and the second inequality we have because it's an increasing sequence. Okay, but now this implies that the sequence of integrals is an increasing sequence in R. And because we allow infinity, well, because the sequence is increasing, either it converges to some real number or it converges to infinity. So we can do the following thing. We can just take this inequality and let n go to infinity. Integral Fn limit n to infinity integral Fn d mu is less than or equal to integral f d mu. Okay, so just because the Fn are all below f, the limit of their integrals has to be below the integral of f. So this was the easy direction. And now to prove the opposite inequality, that's a bit more tricky. Here we really have to use the definition of the integral and to approximate f by simple functions and then do some tricks. So start with a simple function. Phi equals sum j equals 1 to k, aj, characteristic function of sj. So assume this is a simple function, so all the aj are non-negative and the sj are measurable, and assume that phi is less than or equal to f. And in addition, we choose a real number between 0 and 1, c. Okay, so keep this in mind. Now we define the sequence of sets En to be all x in x such that c times phi of x is less than or equal to Fn of x. So first, this is measurable. This can be seen from that's because the Fn are measurable and because phi is measurable, and En is defined by inequalities between these measurable functions. So you can easily see that these are measurable sets. And then, by definition of these En, we have En is a subset of En plus 1. This is easy to see because the Fn are increasing. So if we increase n, then this condition becomes weaker, so the set becomes larger. So En is a subset of En plus 1. And in addition, X, the entire space, is the union of all the En. And this is only true because this constant c is less than 1. Right, so what we've done is we have a fixed function f, and then we have a simple function which is below f, so less than or equal to f, and then we have the sequence that converges to f from below. So because we know that f is less than or equal to f, phi is less than or equal to f, if we decrease phi by a little bit, then these fn will eventually be larger than phi. And that's what we've done here. We've decreased phi a little bit by multiplying it by a constant less than 1. And then we know that, because fn converges to f, eventually fn of x will be larger than phi of x. And that's why eventually every point in x will be in one of the en. And that's precisely this. So yeah, these are the properties of the en. And now look at the following function: c times characteristic function of en times phi. This is again a simple function, right? It's just characteristic function of some set times simple function. That's again a simple function, and then we just multiply it by a number. And we can even write down the representation. This is sum j equals 1 to k, c, aj, chi, en cap s j. Right? We take chi en and multiply this function by chi en. And then chi en times chi sj, that's just the characteristic function of the intersection. Because only when both characteristic functions are 1, the product of them will be equal to 1. So only when x is in the intersection of en and sj, the product will be equal to 1. So the product of two characteristic functions is precisely the characteristic function of the intersection. So this is the representation, this is one representation of this simple function. So now this is simple, and in addition, c chi en phi is less than or equal to fn for every n. This inequality is just by definition of en. Right? And this left-hand side is only non-zero when x is in en because of this characteristic function. But on en, c times phi is less than fn. So this function is always less than fn by construction. And now, because this is less than fn, we can use monotonicity of integrals, and we get integral c chi en phi d mu is less than or equal to integral x fn d mu. Okay, call this equation star. Now, and now what we want to do is, we want to take n to infinity in this inequality, because x is the union of all the en. If we take n to infinity, then this chi en goes away, and we just have c times phi And on the right-hand side, we get the limit of the integrals of the Fn, and that's the thing we want to study, right? We want to get this opposite inequality. So here, in the first step, we proved that the limit of these integrals is less than the limit of the integral of f. And now we have an inequality that says that the integral of the Fn is larger than something. So we just have to do a little bit more work to turn this left-hand side into the integral of f. But that's the plan. So remember this equation. And now, as I just said, we want to take n to infinity. So let's look at this left-hand side. What happens to this left-hand side if we take n to infinity? So integral x c chi en phi d mu. This is, now we use this representation, sum j equals 1 to k c aj chi en cap sj. And from this, we conclude that as n goes to infinity, this converges to sum j equals 1 to k c. Nonsense. This is mu of, mu of en cap sj. Because it's the integral of the function. So where we had the characteristic function, now we have the measure of the set, because we're taking the integral. And now this converges to the sum c times aj times mu of sj. Sanity check, does anyone know why this converges to this? Yeah.
Because En converges to X, so the
Yes, but we are,
intersection will just be S. Okay.
that's the reason, but we're using a theorem. Do you know? It's fine. You don't have to know everything by heart, but it's one. Huh?
Monotone convergence.
Yes, right. It's a theorem we've used many times already. So here we're using the monotone convergence theorem for sets, because the En are nested, right? And whenever we have such a nested sequence of sets, we can use the monotone convergence theorem for sets to conclude that mu applied to this sequence converges to mu of the union. So this is theorem 2.16, monotone convergence theorem for sets. Okay, but now this sum, by definition, is just c times integral phi d mu, right? This was the representation for phi, and now we have this sum. This is just the integral of phi times c. Okay, so now we know what the limit of this left-hand side is. So taking n to infinity in this equation implies that the limit of the left-hand side, c integral phi d mu, is less than or equal to, well, we know nothing about the limit of the right-hand side, so this is just limit integral x fn d mu. But But this inequality now is really handy because phi was an arbitrary simple function which is less than or equal to f. So we can use phi in the definition of the integral of f, right? The integral of f was the supremum over all integrals of such phis. So since phi was arbitrary, it follows that sup integral phi d mu such that phi simple and phi less than or equal to f is still less than, take c to the other side, less than c inverse limit integral f and d. Right, so we've just taken this equation and taken the sup over all phi, which are less than f. By definition, this supremum is just the integral of f. Integral f d mu is less than c inverse limit m to infinity integral f n d mu. And now this inequality holds for every c between 0 and 1. Right? C was completely arbitrary between 0 and 1. So now in the final step we can send this constant c to 1 and we get the inequality for c equals 1. And now this is the opposite inequality, and the proof is finished. Are there any questions about this proof? If that's not, yes.
I think I'm a bit confused about the motivation behind the ENs. Like, I don't understand why you need the ENs. Like, where do we use it?
If you want, I mean, if you want intuition, why you would choose these ENs, I don't know. It's, I mean, you ask why do we have to use them? Maybe we don't have to. I mean, maybe there's a different proof. Who knows?
Okay.
Maybe we don't have to use them, but they work. They're one thing that works. Because they have this property and this property.
When do you use the subset property?
Here, when we apply the monotone
okay.
convergence theorem for sets.
Okay.
Yeah, I don't have a good intuition. The idea is just to use these simple functions to approximate f from below, and then to make your life easier, you make them a little bit smaller. And that way, that allows you to introduce these sets in the first place. Because then all the fn's eventually become larger than c times phi. But yeah, I agree. I mean, at this point in the proof, you don't know where it's going in the end. It's just something. You realize that it works when you're finished. Was that somehow satisfactory?
Yeah, yeah.
Are there any other questions? Okay, so now we continue with several corollaries from this theorem. So the first is, another important convergence theorem. It's called Fatou's lemma. And it says that if you have a measure space x sigma mu and a sequence of non-negative measurable functions then integral lim inf fn d mu is always less than or equal to lim inf integral fn d mu. So now the only important assumption here is non-negativity. So the sequence elements fn have to be non-negative functions, and then we can always take out the lim inf and we have this inequality. So this is quite handy very often. And the proof is quite straightforward because now the hard work is done and we can use the monotone convergence theorem. So the proof is just, okay, define Gn to be the infimum k larger than n fn pointwise. Then the Gn are measurable because we've seen that last time. And this sequence Gn is increasing. It's increasing, it's non-negative, and Gn converges to lim inf fn pointwise. So these functions Gn satisfy the assumptions of the monotone convergence theorem, so we just apply it. And we get that limit n to infinity integral Gn d mu is equal to integral f d mu, but Gn is less than or equal to Fn, so lim inf and to infinity integral Fn d mu is larger than or equal to, well, lim inf Gn, if you like, integral Gn, if you like, and that's the integral of f. Oh, I didn't say what f is. F is this limit by definition. Okay, so the limit of Fn we just call f. And then Gn converges to f. So we have from the monotone convergence theorem, we have this equality, and then this is larger than integral of f d mu. And then if you replace f by the lim inf again, this is precisely the statement of this theorem. So the proof of this is just one idea, namely to define this Gn in a convenient way and then apply the monotone convergence theorem. The next theorem gives us the linearity of the integral. So now we learn all the things that we know from the Riemann integral. X sigma mu is a measure space. F G non-negative measurable functions. Alpha, beta, non-negative numbers. Then alpha f plus beta g is I forgot to say that f and g are measurable. Okay, then alpha f plus beta g is measurable, and integral alpha f plus beta g d mu is the same as alpha integral f d mu plus beta integral g d mu. Note that we still only consider non-negative functions, and also these parameters alpha and beta have to be non-negative in order to retain non-negativity of all these functions, so that we can use our definition of the integral. Maybe we can just manage to do the proof before the end. So the proof of this is rather straightforward. Use the definition of the integral, and use the fact. And yeah, to prove this theorem, we use the fact that we can approximate f and g from below by simple functions. That was a lemma that we proved last time. So the proof is divided into two steps. Step 1, we assume that f and g are simple. So say f has the representation I, sum I equals 1 to k ai characteristic function of some set ai, and g sum I equals 1 to k bi characteristic function of ai, and I'm choosing common sets ai again. So f and g have the same sets ai. Then integral of alpha f plus beta g d mu just by definition is sum I equals 1 to k alpha ai plus beta bi times mu of AI. And now we can just use linearity of the sum. So this is the same as sum I equals 1 to k. We can even put the alpha in front of the sum. So this is alpha times sum I equals 1 to k AI mu of AI plus beta sum I equals 1 to k bi mu of AI. And now these are the integrals of f and g respectively. So this is alpha times integral f d mu plus beta integral g d mu. So this is when f and g are simple. And now step 2. If f and g are just measurable, then as I said, we can approximate them from below by simple functions. So choose sequences phi n that converges to f from below, and psi n that converges to g from below, and phi n and psi n are simple. Then clearly alpha times phi n plus beta times psi n converges from below to alpha f plus beta g, and integral alpha phi n plus beta psi n d mu is the same as alpha integral phi n d mu plus beta integral psi n d mu. This follows from step 1, because phi n and psi n are simple functions. And now we can let n go to infinity. And from the monotone convergence theorem, right, because these phi n and psi n converge to f and g from below, so we can use the monotone convergence theorem. We can just let n go to infinity on both sides of the equation, and then phi n becomes f and psi n becomes g, and we're done. And this is the proof of linearity. So here you can see how useful this monotone convergence theorem actually is. We didn't know whether the integral was linear in the first place, but now from the definition, but now we know it, and the key was the monotone convergence theorem. So we can get these very useful things like linearity from this theorem. Okay, so this is the proof of linearity, and I think time is over. So if you have questions, feel free to ask questions. Otherwise, have a nice weekend and see you next week.